morning, everybody. So I'm Ahmed, Khalil, and Simon Hebert from Delsan. We're discussing the risk analysis that was done for the demolition of the Champlain Bridge. I'll let Simon go into the introduction. We're going to kind of share the presenting of this presentation.
So hi everybody, thank you for being here today. It's an honor for me to represent Delsan-AIM at the event, but also to be once again invited to be a guest speaker at the World Demolition Summit. The Champlain Bridge Construction project is one of the biggest challenges that we have ever worked on at Delsan. And we are really, really proud of all the work that was achieved so far. We started this wonderful endeavor with our partners Pomerleau in July 2020, and all of the work should be completed by the end of this year. Working under the NHSL joint venture, the project will be completed on time, but also in budget. During the execution of the deconstruction work, we have faced multiple challenges, some bigger than others, but all challenges were managed with proper risk management, but also always with the health and safety of our workers as a lead decision maker. The bridge location itself was the main reason of those challenges. The goal was to safely deconstruct a bridge that is 3.4 kilometers long, that is spanning over the St. Lawrence River, linking the southwest of Montreal to the South Shore in the city of Brossard. Obviously, we also had to demolish the bridge by ensuring that there will be no environmental negative footprints at the end of the project, but also that all the workers and nearby residents will be safe at all times. The other big challenges was to manage all materials that were generating on that project. We're talking about more than 250,000 tons of concrete, 25,000 tons of steel, and 12,000 tons of asphalt. Last year, I had the opportunity to present the traceability effort that we made on that project, but this year we'll be really be focusing on the means and methods and the work that ASI done with us on this project. So as I was saying, to tackle some of those risks, we have contacted our friend at ASI to help us successfully many times in past projects. So Ahmed.
So we've worked with Delsan before, and we have a very good relationship and successful relationship. We work with them on the Nanticoke generating station, where we're modeling the collapse of the stacks, and with the Lambton generating station as well, modeling the collapse of the stacks and the induced collapse for the SCR structure. This time they got us involved in the modeling of a bridge. We didn't work on bridges with Delsan before, but we had experience with working with bridges, modeling the collapse of bridges, whether it is an accident like the I-35 bridge in Minnesota or the Morandi bridge in Italy, or whether it's a demolition and induced collapse of a structure, the perimeter bridge in Rio de Janeiro, and bridges in Italy I presented about maybe 5-6 years ago here at the World Demolition Summit. So we're using a technology called extreme loading for structures, and this technology started at the University of Tokyo in 1995, and it's really specific to modeling of the collapse of structures and really successful in modeling of demolition projects. We've modeled demolition projects in 5 continents. This specific project had some challenges, and I think Simon is going to address more of those challenges.
Yeah, so as you can see here in the picture, due to different site conditions that we had to face during the execution of the work, multiple means and methods were used during the demolition process. Within all those methods, we work with ASI to modelize 2 specific methods to control the risk and make sure that our planning was safe at all times and there will be no sudden collapse in the structure. The first of those two methods was what we call method E. Method E is pretty simple. It looks simple, but it consists of a full mechanical demolition of 4 spans that were spanning over an 8-lane highway, plus the shoulders, that needed to be demolished in a single weekend during a single operation. The 4 span, the average length of those spans were 53.7 meters. All of those spans were built the same, which means that they were composed of 7 precast, pre-stressed girders, linked together with a post-tensioning concrete deck longitudinally. And the total of those 4 spans, we're talking about more than 10,000 tons of concrete, if we include the piers, that needed to be demolished in a single weekend. And for us to achieve that milestone, we had to mobilize more than 20 different equipment, including 16 excavators with a demolition attachment. The sequence of the work is a standard sequence for anybody demolishing a bridge over a highway, but there was particularity into that structure that needed ISI work to confirm the assumption that we had during the planning stage of the method. So quickly, basically, we had to close the highway. This is a major highway in Montreal. Is for those working on civil work, it's a challenge itself just by doing that. There were more than 20 different detours to be input just to close the highway. And then we had to install a full general protection with embankment for us to proceed with drops, which will be the subject of Ahmed's work. And then we mobilized the equipment. We demolished simultaneously the 2 edge girder, and then we drop the 3 middle girder in a single operation. And then as soon as the girder were dropped, they were demolished in place, and this operation was repeated 4 times, so we could clear the highway in time for us to reopen before the Monday morning rush. And one thing that is important to understand, and this is what ASI worked on, is that the stability of the span of a single span itself was pretty uncertain because there were almost no rebar in that design. Everything was post-tensioned, and there was a lot of reinforcement work that was done throughout the years. So we weren't able to pinpoint without ASI when we need to proceed the drop, and if we were able to demolish the first H girder and avoid a sudden collapse.
So as Simon mentioned, that they had decided on this is the method we're going to apply, and they were looking at fine-tuning the details that are needed to a certain safety, look at all the risk scenarios. One of those challenges is every span was different, and they had retrofit done to them. We included all of that in our modeling using extreme loading technology. And we included the additional reinforcement, the additional FRP that was added. And we looked at what would trigger the collapse, how many beams for this cross-section, for example, it had 6 longitudinal beams. How many of those can be removed safely before the drop is triggered, and what is the sequence of removing them? Do we start by removing the cross girders here, or the diaphragms, or we start with a different sequence? So we looked at different alternatives, and this is the one that we found when coordinating with the Delsan team, that this is the most safe method to proceed with that specific sequence, leaving the diaphragms till the end to allow for additional lateral stability. And then we proceeded to study every girder. We had information about how much reserve capacity it had due to degradation, and we found that the edge girders were more degraded, so that the decision was to proceed from both sides at the same time, so reducing from this side and that side, because those were the ones that are more degraded, and the ones in the center were left till last. And the number of girders to be left till the end was one of the parameters that we studied to see what is the optimum number of girders that can be safely in place before the drop is initiated. So this is of course, the amazing work that was done in terms of doing all of that work at the same time, and the analysis that was done in the background to make sure that this sequence will proceed safely without unexpected failure of the bridge ahead of the intended drop time. So we're looking at the stresses and the deformations in the bridge beams based on the specific sequence that they were proceeding with. We accounted for, as I mentioned, the additional reinforcement, so we had additional information, things that were added to the bridge after the fact, and the red color here is the additional reinforcement that was added, and the effect of that was taken into consideration when we're measuring the deflections, how much the bridge is going to deflect as we, piece by piece, start removing parts of that bridge. This is the simulation that was done for a case where we try to see how far we can push it. Can we go until we just have one girder standing, or do we need to drop it ahead of that? And it was decided we're not going to go with just like for this specific case, the one drop scenario. We estimated the factor of safety of that and decided we're going to go with a different scenario with more than one beam at the end. Here, this is taking it to the extreme, trying to go with the mechanical demolition till the end, and we're looking at how much it deforms. The chart is showing how much the structure is deforming with time as we start taking parts off of it, and this is how it would collapse if we go with that sequence. And we studied many of those sequences, dozens at least of different sequences to come to the optimum one. So for every scenario that we study, we look at what is the safety factor for this scenario until we get a scenario that is feasible, and at the same time it satisfies the safety factor that is acceptable for us and for Delsan. So that's the final agreed upon sequence of demolition for one of the spans, actually a couple of the spans, and as I said, every span was different, so every span that we studied had to have a different model for it. And this is how it was actually implemented. You can see that we also included the boundary conditions. So it's not just the span of the bridge, it's also how much of the bridge is still continuous at the top and at the bottom of this picture. The rest of the bridge was also taken into consideration in the model, the effect of the remaining parts of the bridge on stabilizing the piers, because we also wanted to make sure that the piers are stable during the drop. So that was also one of the factors that we had to look into and coordinate closely with Delsan. We had the information about the bridge piers, and we included them with their actual dimensions, actual reinforcement in the model. So it's one big model taking all those engineering factors into consideration. For some of the bridges had different like some of the spans had different number of diaphragms, like this specific one, this was the number of diaphragms that were included, and this is how it looked just before the intended drop or the induced collapse for the remaining portion. This is the kind of stress analysis that we do to make sure that it is safe until this point. And then we looked into, now it's showing the additional point, which is kind of controlling the drop when it comes time for the drop, making sure that the impact with the ground is controlled, that it's not causing excessive vibrations, that it's not causing excessive damage to the piers. So that was a very important point for Delsan, and they provided all the information, and they proposed multiple scenarios for where to place the debris pile to control the drop of the bridge and where they're going to make the cut. And for every span, it can be a different scenario. So we looked at multiple scenarios, and we're trying to avoid a scenario like this one. Maybe another click will do the trick. So that was a concern that Delsan had and that we had. We didn't want to see something like that happen. So we wanted to make sure that the drop of the bridge is controlled and the span is dropped, but the piers are not affected. So we did an additional analysis looking at the force on the pier. So from the engineering analysis, we do the cutting, in the bridge, and we see how it's going to drop and what's the height of the debris pile and what's the location of the debris pile. And based on that, on the chart, it's showing the force that is hitting the bridge. For this scenario, the bridge does not collapse, and the force that's hitting the bridge is acceptable for the design of this pier. And we repeated that for the different piers. So for this pier, it's a different impact force, it's a different height of the bridge dropping, and it's a different design for the pier itself. The amount of reinforcement of the pier is taken into consideration, and how much force can this pier take as a lateral hit when the bridge falls and impacts the pier. So we looked at all of that, and we checked with Delsan, and we got multiple scenarios, and for the different spans, we looked at the different scenarios. So this is like a picture straight out from the report that was used for the final plan. We did multiple runs with different risk scenarios, different locations of the debris pile, and different properties of material for the span of the bridge. And based on that, another point that Delsan raised is the debris spread. We wanted to make sure we don't have the debris spread exceeding a certain limit, so we provided, this is the output from the engineering analysis, this is where the spread is going to land, and this is how far from the footprint of the bridge the debris is going to land. And this is the like one of the simulations for one of the bridges. This is how it looked in the analysis that we made available to Delsan to do their planning based on this kind of result. And this is how they actually implemented it. Let me see if this will go. Okay. So the number of beams left, the location of the cut, the debris pile that is placed below, all of that was part of the planning that led to the successful outcome that Delsan is showing here. And this is all for just the one method. I'll just put some side-by-side shots for this method. This is how it happened, and this is how the model was predicting it. We tried to match the angle to have like a similar looking angle. There was another method. There were actually plenty other methods that Simon mentioned, but this is the other method that Delsan required us to do the analysis for. So I'll let Simon introduce this method.
So thank you, Ahmed. So keeping in mind what we just saw, the instability of the actual span where we're actually demolishing it, we had another challenge. It was to remove 30 spans over the St. Lawrence River. One of the main concern that we have was the actual height of the structure. The structure was varying from 15 meters all the way to almost 30 meters up in the air, resting on two single piers with an unstable concrete span. So since we have to deal with that height, and the drop option was not possible because we obviously have to work on barge, we decided to bring the span in a single piece using a self-erecting jacking system that will be installed on a barge, as you can see right here. So the main idea of the span, will show you a nice video at the end of the presentation to show you the actual result, was really to prepare the span for him to be ready to be removed, removing the expansion joint, reinforcement, anything that could be removed before without affecting the integrity of the bridge. And then using a barge, I'm just going to shift to the other picture, which is really more speaking by himself. So, back.
I can do it.
Yeah, okay. Laser.
One more time.
One more time. Sorry for that. So here, as you can see, this is the system with the span on top of it. The actual lift is done at that point. So we install ourselves what we call a winch barge on both sides and also one upstream, so we can control the way that we're going to insert ourselves underneath the spans. The actual tolerance that we have on each side of the piers was 150 millimeters. Okay? So it was pretty tight. So the intent was really, if you look at the sequence, if I go back, So we performed the barge placement, and then we were pushing the platform up with the jacking system, and then the last meter of the weight will be, the transfer of the load will be done by deballasting. So we weren't pushing on the actual bridge with the system, we were removing water from the barge until the point that we had full contact, and we took the entire load of the span on the platform. And then at that point, we pushed the last millimeters with the hydraulic system to lock the system in place, and then using the same barge system that you see here, we were moving upstream with the barge. With the next step was to lower the entire span at the level of the excavator that you see here in the little podium that we built. So at that point, we were able to safely demolish the entire span in a single operation using 2 standard equipment with transport barge placed on both sides to receive and carry around concrete all the way to the shore. So by building that system, we were able to really remove those 30 span in a single piece without risking any sudden collapse of the structure during the work. So again, in order to manage our risk and make sure that the system itself will behave like we thought, we give a mandate to RSI to verify the behavior of the actual concrete span, but also his interaction with basically the bridge, the steel bridge that we built underneath that will receive also the weight of the span, and all the deformation that was coming from that span that was transferred to the barge also needs to be validated. So this is why we mandated ASI to look on the force that was done, and Ahmed will explain in detail his work that was performed for that.
So one of the concerns that Delsan raised is the force on the bearings. As they start to lift off the bridge, there was a concern about the amount of friction at the original bearing of the structure. For every beam, we were looking at, as it starts to lift off, how much friction is being generated and whether this is going to be a safe operation or the friction is going to be high and affect the way the bridge lifts off. So that was one of the aspects. Same thing, we focused in our modeling on the aspects that Delsan was most concerned about. Another point was the stresses in the existing bridge as it starts to lift off. Because the location of the support is being moved, we're taking it off its original support and we're supporting it at a different point. So it's stressed in a different way. It behaves in a different way now that it's supported on those new jacking supports. So you can see the stress is readjusting or changing inside of the structure, and we're making sure that those new stresses are still safe for the bridge, because now it's sitting on different kinds of support. So we're looking at, during the lifting process, you can see that stress is shifting from one edge of the structure. The compression stress is moving to a different location because we now have new supports. So that's one other aspect that we looked at. Furthermore, we looked at like the internal forces throughout the length of the bridge for the different spans, because the spans had differences. There were different retrofit done for different spans, so we allowed for the information that was included in the design drawings and in the rehabilitation drawings throughout the years were taken into consideration to look at what is the force, what is the shearing force, what is the bending moment in every component of the bridge as it starts to be lifted. And this is kind of an overview for one of the spans, and there is another one overview as well. So this is kind of a summation of everything that was looked at. We were looking at the separation or the distance between the lifting platform and the bridge itself. So we're seeing the motion of both of them. This is ahead of time. This is how much each one of them is going to deform. We wanted to make sure they don't come into contact at points that we do not intend them to come into contact at, just because one of them is deforming and the other one is deforming the other way, they can come into contact, so we're checking for that. And then we looked at, now for the multiple beams, the internal forces for each one of those beams. We looked at the behavior at the location of the connection, the additional effect of the slabs, the behavior in the top slab, the stresses in the top slab, and then, of course, I've mentioned earlier the behavior of the connection as it starts to lift off. So we repeated the same exercise for different spans, because every span is different, and for every one we're getting different numbers, but we're always making sure that the factor of safety is still acceptable, and performance, the amount of deformation that we're seeing, is satisfactory, and Delsan has no issues with this is what they expected, this is the kind of motion that they are expecting to see during the lift-off process. So that was kind of the summary for every span that we studied. We had to do something similar like that, and then this is how it actually went. I'll let Simon explain more.
So this is a time lapse that was shortened in like a 30 seconds video. The intent is really first to show the behavior of the platform comparing to the model that was done by SI, but also to show you the work that was done and all the thinking that was also performed for us to be able to achieve this method. So we'll have a closer look right here. So that's the platform going up.
It's repeating one more time.
Yeah, it's okay. So this is exactly what we were talking about. We're going up, then we're proceeding with the load transfer by deballasting, and then the last push was done hydraulically. This is exactly what we're seeing now. Then the barge will be moving upstream. We don't have this shot, and then going down, and then the actual span were demolished right in place. So that will be the conclusion of our presentation. Again, we want to thank ASI for the work that they done for us on the project. We're really proud of what we achieved on that project so far. It will be concluded at the end of the year, as I mentioned before. And for us, the key of our success on that project was first to develop a strong communication with all the stakeholders, because there were a lot of people involved, including the federal government, provincial government, the Seaway Corporation, many cities and boroughs, and also the owner of the bridge, which was GCCBI. Everything passed through a project planning that is built around safety, effective risk and change management process. Obviously, in a 3-year project, there's a lot of change, a lot of unknowns, so we have to be prepared and ready to face those change and those risks. Obviously, strong engineering and modeling was also the key of our success, and also quality and environmental monitoring on an everyday basis guarantee that we didn't have any negative impact for the community surrounding the project. Thank you.
Thank you, gentlemen, very much for that presentation. We have some time for one question from the audience, if the microphones can go out. And, there's a question in the front here.
Thank you. Thanks, Delsan.
Did anything go differently to what you expected? Smiling some of the things that happened. I was thinking that it's not going to get jumped when it failed. So did anything happen that didn't expect?
For us, no. I think Delsan may.
Operational-wise, no, everything went as planned because of the work that we done before, as I said. So the planning was the key of the operation here.
Well done, fellas. Good job.
Thank you.